morning, tutor. So glad to be back for another deep dive.
Good morning. Ready to jump in?
Absolutely. Today, we're diving into Unit 1 of Chemistry, some basic concepts of chemistry.
The foundation.
Exactly. I know this unit is often seen as just the intro, but for our Class 11th board exams, and especially for competitive exams like JG and NEET, I feel like it's the absolute bedrock.
You're spot on.
It sets the stage for everything else, you know? I'm really keen to solidify these foundations.
Good thinking. And you've hit the nail on the head. Basic concepts isn't just an introduction. It's the very grammar of chemistry. Think of it as learning your ABCs before you can write, well, anything complex.
Right.
Mastering this unit is absolutely crucial. It's where you build that strong conceptual base needed to, solve those tricky numerical problems and complex theoretical questions that are staples of J and NEET. So we'll go topic by topic, making sure every concept is crystal clear and highly relevant for your exam preparation. Let's start with the fundamental question. What even is science, and where does chemistry fit in? Okay, so at its core, science is, well, a disciplined human effort. It's about systematically organizing knowledge to help us understand the natural world around us.
Okay.
We see countless changes every single day, don't we? Milk turning into curd, sugarcane juice fermenting into vinegar, or that common sight of iron rusting.
Yeah, everyday stuff.
Exactly. These aren't random occurrences. They're natural processes governed by laws that science seeks to unravel. And for our convenience, science is broadly divided into fields like physics, biology, geology, and of course our focus today, chemistry.
Got it.
Chemistry then takes a special seat. It's the branch of science dedicated to understanding material substances, how they are prepared, what their properties are, their intricate structures, and crucially, how they react with one another.
So it's about how stuff is made and how it changes.
Essentially, yes. Chemistry is the science of molecules and their endless, fascinating transformations. It's not just about the roughly 100-odd elements we know, but about the virtually infinite variety of molecules and compounds that can be built from them, constantly interacting and changing. It's like a colossal Lego set, really, where the possibilities are truly endless.
That analogy helps a lot. Thinking of it as a Lego set makes perfect sense. Tutor, it's genuinely interesting to me how chemistry has actually evolved over centuries. Could you give us a glimpse into its historical roots, especially India's contributions? Our textbooks mention it, but I don't always grasp the full picture.
You're right to be curious. While modern chemistry, with its precise measurements and systematic theories, largely took shape in 18th century Europe, its underlying impulses, well, far older.
Okay.
Early chemical pursuits were often driven by what might seem like mythical quests today, like the search for the philosopher's stone, known as paras in some traditions, believed to transform base metals into gold.
Ah, alchemy.
Pretty much. Or the quest for the elixir of life, a potion supposedly promising immortality. These dreams, as fanciful as they sound now, pushed early practitioners to experiment, observe, and document.
Right.
What's truly remarkable and often overlooked is the advanced chemical knowledge that flourished in ancient India, long before what we call modern science.
Right.
This wasn't just abstract theory, it was practical, integrated into daily life.
Oh, really? Like what?
Well, chemistry in ancient India was known by names like Rasayan Shastra, Rastantra, Raskriya, or Rasvidya. It encompassed everything from metallurgy and medicine to cosmetics, glassmaking, and dyes. It was a much more holistic approach to understanding and manipulating materials.
Wow.
We find compelling evidence of this through archaeological digs. Sites like Mohenjo-Daro and Harappa show extensive use of baked bricks. That's an early form of mass chemical processing, right? Involving mixing materials, molding, and heating them to achieve durability.
I see.
There's also evidence of glazed pottery and gypsum cement, revealing an understanding of material science way back then. And ancient Indian metallurgy was exceptionally sophisticated. The Harappans, for instance, they weren't only skilled at melting and forging metals like copper, lead, silver, and gold, but they also knew how to improve copper's hardness by adding tin and arsenic. That shows an early grasp of alloy formation. It wasn't accidental. It implied systematic experimentation.
That's amazing.
Beyond metals, consider glass and dyes. Glass objects unearthed in Maski in South India, dating back maybe 1,900 BCE, and sites like Hastinapur and Taxila in the north, show early glass production and, importantly, the use of metal oxides for coloring. That's foundational inorganic chemistry right there. Ancient texts, too, are treasure troves. The Rig Veda mentions leather tanning and cotton dyeing. The famous golden gloss of black polish ware from northern India dating back centuries is still kind of puzzles chemists today, hinting at a profound mastery of kiln temperatures. Kautilya's Arthashastra detailed salt production from the sea. And monumental works, like the Sushruta Samhita and Charaka Samhita, describe preparing various acids like sulfuric and nitric acid, along with oxides and sulfates of metals like copper, tin, zinc, and iron.
It's really advanced stuff.
Absolutely. Even concepts akin to nanotechnology, like using metallic bosons for medicine, were discussed in the Charaka Samhita. Modern science now confirms these often contain nanoparticles.
Incredible.
From an exam perspective, remember that this history shows that foundational chemical principles like material transformations, fixed compositions, understanding different states were being explored globally, not just in Europe.
Right.
While India had this strong base, the 20th century saw a bit of a decline as Western medicine gained dominance, and it took time, maybe 100 to 150 years, for modern techniques to be widely adopted here. But this ancient wisdom reminds us chemistry is an enduring human quest.
That's a truly rich narrative, Tutor. It makes me feel, well, quite proud of our historical contributions and reminds me that science isn't just a recent thing. It's been part of human progress for millennia. But zooming back to today, how does chemistry impact us directly, and why is it so intertwined with almost every other science?
That's the perfect question to ask. Chemistry's role today is absolutely central. It's like the bridge connecting virtually all scientific disciplines.
How so?
Well, whether we're talking about intricate weather patterns, the complex functions of your brain, how a computer operates, or the massive scale of chemical industries, chemistry is the silent force at work. It's everywhere, influencing our lives in ways we often don't even realize.
Okay.
In terms of meeting human needs, chemistry is indispensable. Think about our food supply. Fertilizers, pesticides, and insecticides, all products of chemical innovation, have revolutionized agriculture, letting us feed billions. In healthcare, chemistry has gifted us life-saving drugs, from isolating compounds from plants to synthesizing entirely new molecules. Drugs like cisplatin and Taxol for cancer therapy or AZT for AIDS patients are direct triumphs of chemical research.
Right.
And it's not just about health and food. Chemistry is a major engine for national development and economic growth. Our understanding of chemical principles allows us to design and synthesize materials with tailor-made properties, superconducting ceramics, conductive polymers, optical fibers. These are all results of chemists pushing boundaries. Industries producing acids, alkalis, dyes, polymers, metals contribute significantly to the economy and create millions of jobs.
I see.
We're also on the front lines of environmental solutions. Remember CFCs, the chlorofluorocarbons that damage the ozone layer? Chemists develop safer alternatives, helping mitigate a global crisis.
Yeah, I remember learning about that.
We still face immense challenges, though. Managing greenhouse gases like methane and carbon dioxide, developing sustainable energy. These aren't just scientific problems, they're societal ones. A developing country like India urgently needs talented, creative chemists to innovate and solve these grand challenges.
Definitely.
And to truly excel in chemistry and tackle these problems, you absolutely must grasp its basic concepts, starting with the most fundamental building block, matter.
So we're talking about matter as the fundamental building block. Could you start by defining what matter is and then explain its common states?
Absolutely. The very foundation of chemistry begins with matter. It's incredibly simple yet profound. Matter is anything that has mass and occupies space.
Okay, mass and space.
Exactly. Look around you right now, your textbook, your pen, the water in your glass, the air you're breathing, even you yourself, and all living beings, every single one is composed of matter. They all have a specific mass. They all take up a certain amount of space. Now, matter commonly exists in three physical states that you've likely encountered many times: solid, liquid, and gas. What distinguishes them boils down to how their constituent particles, whether atoms or molecules, are arranged and how much freedom they have to move. Let's visualize this.
Okay.
In solids, the particles are held extremely close to one another in a very orderly, often rigid arrangement. They have very little freedom to move. They mostly just kind of vibrate in their fixed positions.
Right, like in a crystal.
Precisely. Because of this tight, organized packing, solids have a definite volume and a definite shape. Think of a stone, a block of wood, or ice cubes. They maintain their form regardless of the container.
Makes sense.
Moving on to liquids, the particles are still relatively close, but they have much more freedom. They can slide past one another, constantly shifting their positions. This fluidity is why liquids have a definite volume, but they do not have a definite shape.
They take the shape of the container.
Exactly. They gracefully take the shape of the container they are placed in. Pour water from a jug into a glass. The volume remains the same, but the shape changes. Finally, in gases, the particles are very far apart from each other, much more so than in solids or liquids.
Yeah.
They move easily and rapidly in completely random directions, constantly colliding with each other and the container walls.
Total chaos.
Sort of. As a result, gases have neither a definite volume nor a definite shape. They will expand to completely occupy the entire space of whatever container they are placed in. Think of the air filling a room, or the gas in a balloon that fills every corner.
Okay.
A key point to remember for your exams and for understanding real-world processes is that these three states are interconvertible. You can transform one state into another simply by changing conditions like temperature and pressure.
Like melting ice.
Exactly. Heat a solid, it melts into a liquid. Heat the liquid further, it vaporizes into a gas. And the reverse applies. Cooling a gas condenses it into a liquid, and further cooling freezes the liquid into a solid. This dynamic interconversion is a fundamental concept.
That's a clear distinction between the states. So once we understand what matter is, how do chemists classify it at a broader, perhaps more chemical level?
Great question. When chemists look at matter at a microscopic or bulk level, they classified it in two primary categories: mixtures and pure substances. This is a critical distinction for understanding chemical composition.
Okay, mixtures and pure substances.
Let's start with mixtures. A mixture is formed when two or more pure substances are combined in any ratio, meaning their composition can be variable. The individual pure substances that make up a mixture are called its components.
Like salt water.
Perfect example. Or think of the air we breathe, a mix of gases, or even a simple cup of tea. A defining characteristic of mixtures is that their components can typically be separated using relatively simple physical methods.
Like filtering.
Yes, or hand-picking, crystallization, distillation. Things that don't involve changing the chemical nature of the components.
Got it.
Now, mixtures are further divided into two types. Homogeneous mixtures. In these, the components are completely mixed and uniformly distributed throughout. The composition is uniform everywhere. A sugar solution is a perfect example. Once dissolved, every drop is the same. Air is another excellent example.
Okay, uniform. Heterogeneous mixtures. In contrast, these do not have a uniform composition. You can often see the different components. Imagine mixing salt in sugar crystals, you see both. Or grains mixed with dirt. These are heterogeneous. The properties vary from point to point, right? Like lumpy gravy.
Oh, yes, perhaps. Now, let's talk about pure substances. These are fundamentally different. In a pure substance, all constituent particles are chemically identical, and they always have a fixed and definite composition.
Fixed composition.
Exactly. Examples: pure copper, pure silver, pure gold, water, HER, or glucose. Glucose always contains carbon, hydrogen, and oxygen in a fixed ratio. Unlike mixtures, you can't separate components of a pure substance by simple physical methods. You need chemical reactions. Pure substances themselves are further categorized into elements and compounds. Elements. The simplest form of a pure substance made up of only one type of atom, like sodium, Na, or copper.
Okay.
Or they can exist as molecules of the same element, like H0, N0, O0. The crucial point: atoms of different elements are fundamentally different.
Okay, compounds. Formed when two or more atoms of different elements combine chemically in a definite fixed ratio. This ratio is its fingerprint. What's fascinating is that the properties of a compound are completely different from its constituent elements, like the water example.
Precisely. Hydrogen gas is flammable. Oxygen gas supports combustion, but combine them and you get H2O water, which puts out fires. This radical transformation is a hallmark of forming a compound. It's chemical magic, in a way. #33. Properties of matter and their measurement.
So we've classified matter. When we actually study these substances in the lab or in problems, how do we describe them using their properties, and how do we quantify those properties?
Excellent next step. Every substance possesses a unique set of distinguishing characteristics or properties. We broadly classify these into two types: physical and chemical.
Physical and chemical, okay.
Physical properties are those you can measure or observe without changing the identity or chemical composition of the substance. Think about measuring the color, odor, melting point, boiling point, or density. When you measure water's boiling point, it's still water. Its chemical nature hasn't changed.
Right.
On the other hand, chemical properties are those whose measurement or observation requires a chemical change to occur. For example, to know if something is combustible, you have to try burning it a chemical reaction.
Okay, so a reaction has to happen.
Exactly. Assessing reactivity with acids or bases, determining acidity or basicity, these all involve the substance undergoing a chemical transformation. That's the key distinction.
Got it.
Chemists rely heavily on knowing both types of properties, determined through careful measurement and experimentation. This allows them to describe, interpret, and predict behavior. And this brings us directly to a fundamental aspect: quantitative measurement.
Right, the numbers.
Precisely. Scientific investigation, especially for competitive exams, requires quantitative measurement. Many properties' length, mass, volume are quantitative. And here's the absolutely critical part for numerical problems. Any quantitative observation is always represented by a numerical value followed by its units.
Number and unit, always.
Always. Saying a length is 15 is meaningless scientifically. Is it 15 centimeters, meters, inches? You need the unit?
Yeah.
15 centimeters.
Okay.
Historically, there were different systems, like the English and metric systems. The metric system based on decimals became popular. But for global consistency in science, the International System of Units, SI, was established in 1960. This is the system you must use for GG, NEET, and your boards.
SI units, yes. Very important. Could you walk us through the base units and their definitions? I know some of the newer definitions based on constants can be a bit abstract.
Absolutely. Understanding the SI base units is crucial. There are 7 fundamental base units. All of the units are derived from these. Let's list them clearly. 1, length. The SI unit is the meter, symbol M. 2, mass. The SI unit is the kilogram, symbol kg. 3, time. The SI unit is the second, symbol S. 4, electric current. The SI unit is the ampere, symbol A. 5, thermodynamic temperature. The SI unit is the Kelvin, symbol K. 6, amount of substance. The SI unit is the mole, symbol mole. 7, luminous intensity. The SI unit is the candela, symbol CD.
Okay, those 7.
Now let's touch on the modern definitions of a few key ones, as they show incredible precision and are tied to fundamental constants. This is where it gets really interesting.
Right, they changed some recently.
They did. Take the meter. It's no longer based on a physical bar. It's defined by the speed of light in a vacuum, a universal constant. Let's break this down. The meter is defined by how far light travels in a vacuum in a specific tiny fraction of a second. It's fundamentally linked to nature itself.
Wow. Okay.
The kilogram also changed. No more physical cylinder. It's now defined via the Planck constant, the cornerstone of quantum mechanics. This is a bit more complex, but think of it like this. The kilogram is now defined through a fundamental constant of nature, linking mass directly to the quantum world. It's truly universal and stable.
Based on Planck's constant. Okay.
And the second, our unit of time. It's defined by the vibrations, specifically a hyperfine transition frequency of a cesium-133 atom. That's why atomic clocks are so incredibly precise.
Atomic clocks, right.
Finally, the mole. Extremely important for us, so pay close attention. 1 mole contains exactly 6.022140076 1-mile elementary entities. This fixed number is the Avogadro constant. We'll dive deep into the mole later, but its definition is now exact.
6.022 times 10 to the 23. Got it.
All other quantities like speed m's, volume m, density kg are derived from these base units.
Okay.
To handle very large or small numbers, SI uses prefixes, vital for exam calculations. You absolutely need to know common ones like kilo, 10 illo, 1,000, milli, 10 ilohan, 10 millionth, meno-n, 10 illo, billionth, pico pu, dens femto, f demo f. These make writing huge or tiny numbers manageable.
Right, like nanometers.
Exactly. And just for context, maintaining these standards is the job of national labs, like the National Physical Laboratory, NPL, in New Delhi for India. They ensure our measurements align globally.
Now let's look at some specific properties we'll encounter regularly in problems. Mass and weight, for instance. I know they're often used interchangeably, but there's a key distinction, right?
You're right. That's a classic point of confusion. Let's clarify it. Mass is the amount of matter in an object. It's constant. Your mass is the same on Earth or the moon.
Okay, amount of stuff.
Weight, however, is the force of gravity on that mass. Since gravity varies, less on the moon, your weight changes, but your mass doesn't.
Force of gravity, got it.
In the lab, we measure mass accurately using an analytical balance, often in grams, 1 kilogram, 1,000 grams, because we use small amounts.
Okay.
Next, volume. Space occupied. SI unit is mLA-TO. But in chemistry, we often use CMLO or DMLO, and very commonly the liter, L. Remember these key equivalences. 1 L is 1,000 mL equals 1,000 CML is 1,000 cm.
1 liter is 1,000 centimeters cubed.
Right. We use tools like graduated cylinders, burettes, pipettes, volumetric flasks to measure volume, depending on the precision needed. Imagine a 1-liter water bottle that's the scale. Density ties mass and volume together, defined as mass per unit volume. SI unit is kilo-MLO, but we often use GCMLO. Density basically tells you how tightly packed the particles are. Higher density means more packed.
Okay, mass over volume.
Lastly, temperature. 3 common scales: Celsius, degrees C, Fahrenheit, degrees F, and Kelvin. Kelvin is the SI unit. You need the conversion formulas for exams. 3F, degrees C, plus 32, K equal degrees C, plus 273.15.
Okay, need to remember those.
A key thing about Kelvin: no negative temperatures. 0 Kelvin is absolute zero, the theoretical lowest possible temperature. Useful concept for later studies?
Tutor, chemistry often involves dealing with unbelievably huge numbers like Avogadro's number or incredibly tiny masses. How do we even manage to write and calculate with these efficiently without getting lost in, like, a sea of zeros?
You've hit on a practical challenge every chemist faces. Imagine writing out the number of molecules in just 2 grams of hydrogen gas. It's roughly 6, followed by 23 zeros.
Impossible.
Or the mass of 1 hydrogen atom.
Yep.
0 point, then 23 zeros, then 166 grams. Writing these and calculating with them is just asking for mistakes.
Definitely.
This problem is elegantly solved using scientific notation, also called exponential notation. In this system, any number is expressed as n I 10. Here, n is an integer exponent, positive or negative, and n is a number between 1 and 10, strictly 1.0000 to 9.999. So n always has just one non-zero digit left of the decimal.
Okay, n times 10 to the n.
Let's see how it works. Take a large number, say 232.508. Moves to the decimal left until only one non-zero digit remains before it. 2.32508. We moved it 2 places left, so the exponent n is plus 2. Thus, 232.508 equals 2.32508 by 10 list.
Got it. Left is positive exponent.
Right. Now, for a small number like 0.00016, move the decimal right until you get 1.6. We moved it 4 places right, so the exponent n is -4. So 0.000016 equals 1.6 by 10 over.
Right, means negative exponent. Okay.
Positive exponent means big number, negative means small number. Simple check. Now for calculations, multiplication, division. Follow exponent rules. Multiply the n terms that add the exponent. For example, 6.9 by 10 over n sine 3. 10 over L by bam minus 3 equals 17.25 to 10 to 10. Then adjust to standard form. 1.725 by 10. For division, divide n terms, subtract exponents.
Multiply n's, add exponents. Divide n's, subtract exponents.
Exactly. Addition, subtraction. This is slightly different. The numbers must first have the same exponent. To add 6.65 to 10 minus times 10 4, make exponents match. Let's use 10 8. So 8.95 10 minus becomes 0.895 by 10 8. Now add the n terms. 6.65 plus 0.895 times 10 minus equals, as said, by 10 8 each other. Think of it as lining up decimal points.
Okay, make exponents same, then add or subtract n's.
Perfect.
Okay, that makes scientific notation much clearer. This ties into how we report results, right? What are significant figures and why are they so important for precision? This feels like a common source of silly mistakes in exams.
You're absolutely right. Significant figures, or sig figs, are a cornerstone of reporting scientific data accurately. And yes, they are a common trap in JEE and NEET. Every measurement has some uncertainty due to instrument limits and, well, human skill.
Right.
For example, a simple balance might give 9.4 grams, but an analytical balance might give 9.4213 grams. The digits you're sure of, plus one uncertain digit, are the significant figures.
Certain digits plus one uncertain.
Exactly. So significant figures are the meaningful digits known with certainty, plus the last estimated digit. Uncertainty is usually a 1 in that last digit. Reporting 11.2 millilal means 11 is certain, 2 is estimated. It communicates precision. Okay. Now, the rules for determining significant figures. Let's go through these slowly. They're crucial for exams. 1. All non-zero digits are significant. Easy. 285 centimeters has 3 sig figs, 285. 0.25 millimil has 225. Okay. 2. Zeros preceding the first non-zero digit are not significant. They're just placeholders for the decimal. So 0.03 has only 1 sig fig, the 3. 0.00052 has 2, the 5 and 2. Leading zeros don't count. Got it. 3. Zeros between 2 non-zero digits are significant. These are sandwich zeros. 2.005 has 4 sig figs. Zeros in the middle count. Okay.
Yeah.
4. Zeros at the end or right of a number are significant if they are to the right of the decimal point. So 0.200 is the 3 sig figs. But if there's no decimal point, terminal zeros are ambiguous. 100 could be 1, 2, or 3 sig figs. That's tricky.
It is. The best way to avoid ambiguity is scientific notation. 100 can be 1 I 10 per nano, 1 sig fig, 1.0 at 10 planos, 2 sig figs, or 1.00 at 10 to minus 3 sig figs. Very clear. Okay, scientific notation helps there. 5. Exact numbers have infinite significant figures. These come from counting 2 balls, or definitions, 1 inch equals 2.54 centimeters. They're perfectly known, so infinite sig figs, like 2-point numbers. Infinite for exact numbers.
Right.
I often get tripped up on the difference between precision and accuracy. Can you clarify that with a simple example that makes it stick?
Very common confusion, but critical for analyzing data. Let's make it clear. Precision is about consistency. How close are repeated measurements to each other? If you measure something 5 times and get 1.95 grams, 1.93 grams, 1.96 grams, 1.94 grams, 1.94 grams, those are precise because they're tightly clustered.
Okay, close to each other.
Accuracy is about correctness. How close is your measurement to the true or accepted value? If the true value was 2.00 grams, those precise measurements, around 1.95 grams, are not accurate.
Close to the real value. Okay.
Let's use the dartboard analogy. Bullseye is the true value. Darts tightly clustered in the corner. Precise but not accurate. Darts scattered all over. Neither precise nor accurate. Darts tightly clustered around the bullseye. Both precise AD accurate.
Okay, that visual helps a lot. Precise is clustering, accurate is hitting the target.
Exactly. Now, when you calculate with measurements, you need rules for reporting the answer with the right sig figs, addition and subtraction. The result's decimal places are limited by the number with the fewest decimal places. Example, 12.11, 2 places, plus 18.01 place, plus 1.012, 3 places, equals 31.12. Report as 31.1, limited by 18.01 decimal place.
Fewest decimal places for adding, subtracting.
Correct. Multiplication and division. The result significant figures are limited by the number with the fewest significant figures. Example, 2.5, 2 sig figs, a 1.25, 3 sig figs, equals 3.125. Report is 3.1, limited by 2.5's 2 sig figs.
Fewest significant figures for multiplying, dividing.
Okay. And finally, rounding off numbers. Pay close attention here, especially to Rule 3. 1. If the digit to remove is 5, round up the preceding digit. 1.386 rounds to 1.39. 2. If the digit to remove is 5, don't change the preceding digit. 4.334 rounds to 4.33.
Standard rules. 3. If the digit to remove is exactly 5. 3. If the digit to remove is exactly 5, if the preceding digit is even, don't change it. 6.25 rounds to 6.2. 3. If the digit to remove is exactly 5, if the preceding digit is odd, round it up. 6.35 rounds to 6.4. The even odd rule for 5. That's one I forget. Keep even. Round up odd.
Precisely. That specific rule for 5 is very important for exams.
That makes perfect sense, especially that rule for rounding off with 5. That's a classic trap. Now, speaking of calculations and conversions, dimensional analysis is super useful. Could you walk us through that method? I always prefer a systematic approach for conversions.
Absolutely. Dimensional analysis, or the factor label method or unit factor method, is incredibly powerful and reliable for converting units. It ensures units cancel correctly, guiding you logically. It's indispensable for Jeanette to minimize errors.
Okay, sounds good.
Let's walk through the logic with a couple of examples. Detailed numbers are in your notes. Example 1, inch to centimeter.
Convert 3 inches to centimeter.
Equivalence. We know 1 in inch is 2.54 centimeters. This is our bridge. Unit factors. From this, we get 2 fractions equal to 1. 2.54 centimeters, 1 inch, and 1 and 2.54 centimeter.
Right, like conversion factor.
Multiply. We want to cancel inches and get cm, so we need in the denominator. Use 2.54 centimeters.
So 1 inches.
2.54 centimeters, 1 inch. See, so in cancels. Yeah, inches on top and bottom cancel out.
Leaving you with centimeters, the result is 7.62 centimeters. Choose the factor that cancels the unwanted unit.
Okay.
Example 2. Liters to cubic meters.
Convert 2 whittles of milk to m.
Equivalences. 1 L, it was 100 centimeters and 1 meters, and 1 meter is 100 centimeters.
Okay.
Volume equivalence. Cube the length 1. 1 meter L equals 100 centimeters, and 1 meter equals 10 centimeter.
Right. Cube everything.
Convert L to center. 2L is 1,000 centimeter to C10. Convert cm or 2 ns to in meter. We need cm in the denominator. Cancel. Use 1 meter or 2 na. It's 1 meter 10 centimeter. Result is 2 pn or an.
Got it. Chain the conversions.
Exactly. Example 3. Days to seconds.
How many seconds in 2 days?
Chain factors. Days, hours, ever minutes,
Yep.
60 minute. 24 hours 1 day. 60 minute away. 64 hours.
Right.
Multiply. 2 days, x. 24h, 1 day, x 60 minutes, 1 name, x 16th minutes. Notice how days, then hours, then minutes cancel, leaving seconds.
Beautifully cancels out.
The calculation gives 172,800 plas. The beauty is treating units like numbers they cancel, multiply, divide, get squared. Master this and you'll nail many exam problems.
Tutor, so far we've talked about matter and how we measure it, but how elements actually combine to form compounds isn't random, right? What are the fundamental laws that govern these chemical combinations?
That's the perfect transition. You're absolutely right. Chemical reactions aren't arbitrary. They follow specific rules. Before Dalton's theory unified things, these observations were codified into 5 basic laws, laying the groundwork for modern chemistry.
Okay, 5 basic laws. First, the law of conservation of mass, proposed by Antoine Lavoisier in 1789. Through meticulous experiments, especially on combustion, he concluded, in any physical or chemical change, matter is neither created nor destroyed.
Mass stays the same.
Exactly.
Yep.
Total mass of reactants equals total mass of products. This is why we balance equations. It's bedrock.
Next, the law of definite proportions, or definite composition, by Joseph Proust. He observed that a given compound always contains exactly the same proportion of elements by mass, regardless of its source.
I'll lay the same recipe.
Precisely. His classic example was cupric carbonate natural versus synthetic samples had identical compositions, CO percentages. Fixed composition is unique to a pure compound.
Okay.
Building on that, the law of multiple proportions, by John Dalton, 1803. This is a bit more nuanced. If 2 elements form more than one compound, the masses of one element that combine with a fixed mass of the other element are in a ratio of small whole numbers.
Okay, explain that one more.
Sure. Classic example. Hydrogen and oxygen form water, HOO and hydrogen peroxide, water. 2GH combines with 16GO peroxide. 2GH combines with 32GO. See how we fixed the mass of hydrogen at 2G? Now look at the oxygen masses, 16G and 32G. What's the ratio? 16.32.
A simple whole number ratio.
Exactly. That simple ratio 1.2 for the second element when the first is fixed is the essence of this law. It was crucial evidence for atoms.
I see now. Fixed mass of one, ratio of the other.
Perfect. Then comes Gay-Lussac's law of gaseous volumes, 1808. He observed that when gases react or are produced, they do so in simple ratios by volume, provided all gases are at the same temperature and pressure.
Like definite proportions, but for volumes of gases.
Exactly. For example, 100 milliliter hydrogen plus 50 milliliter oxygen, 100 milliliter water vapor. The combining volumes, 100 milliliter and 50 milliliter, are in a simple 2.1 ratio.
Okay. Gay-Lussac's law seems to hint at something about how molecules behave. How did Avogadro explain this observation, which feels very foundational?
That's a very insightful connection. Gay-Lussac's law was a puzzle for Dalton's original theory. The breakthrough came with Avogadro's law, 1811. Avogadro made a revolutionary distinction between atoms and molecules. Dalton thought atoms of the same kind couldn't combine, so he couldn't explain things like H or O.
So Dalton missed molecules.
Essentially, yes, for elements. Avogadro proposed that equal volumes of all gases at the same temperature and pressure contain an equal number of molecules.
Equal volumes, equal molecules.
Exactly. Let's revisit Gay-Lussac. 2 volumes H plus 1 volume O, 2 volumes water vapor. If we assume diatomic molecules H and Oros and water is HO as Avogadro did, 2Hg plus OG, 2H-Ordo, suddenly it works. 2 volumes or molecules of H react with 1 volume or molecule of Odo to give 2 volumes or molecules of HO. The volume ratio 2.1.2 is perfectly explained by assuming molecules.
Wow, okay, that clicks.
It was a huge insight. Though not immediately accepted, Stanislaw Cannizzaro revived it later, cementing its importance.
So all these laws about mass, fixed ratios, whole numbers, and volumes ultimately pointed towards something fundamental about matter. And that's where Dalton's atomic theory comes in, right? What were its main points and what did it explain?
Precisely. These empirical laws were the evidence leading to Dalton's atomic theory, 1808. While the idea of atoms, atomio, indivisible, was ancient Democritus, Dalton formalized it scientifically.
Okay, what did Dalton propose?
His main postulates, crucial for exams. 1. Matter consists of indivisible atoms, the fundamental particles. 2. All atoms of a given element are identical in mass and properties. Atoms of different elements are different. 3. Compounds form when atoms of different elements combine in fixed, simple whole number ratios. Explains definite proportions. 4. Chemical reactions involve reorganization of atoms. Atoms aren't created or destroyed, just rearranged, explains conservation of mass.
Seems to cover the laws we just discussed.
It did, remarkably well for its time. It was revolutionary. But, like all theories, it had limitations. It couldn't fully explain Gay-Lussac's volume law because it missed diatomic molecules initially, or why atoms combine. Those came later. But Dalton provided the essential framework.
So we know atoms are these fundamental tiny particles, but how do we even begin to measure their masses? They're incredibly small, almost unimaginable.
That's a fundamental question. You're right. Atoms are exquisitely small. Today, we have sophisticated techniques like mass spectrometry for precise measurements. But historically, 19th century scientists couldn't weigh single atoms, so they determined masses relative to each other. Initially, hydrogen, the lightest, was set to 1 and others were compared to it.
Okay, a relative scale.
The present system, since 1961, uses carbon-12 as the standard. RIC is assigned a mass of exactly 12 atomic mass units, AMU. All other atomic masses are relative to this.
Carbon-12 equals 12 AMU.
Okay, so what is one atomic mass unit, AMU? Let's define it carefully. It's exactly 112, the mass of one carbon-12 atom. It's incredibly small, about 1.66, sometimes 10 urograms. A hydrogen atom is about 1.00080 AMU.
Wow, tiny.
Nowadays, AMU is often replaced by U for unified mass. You'll see both.
U or AMU, got it.
Now, when you look at atomic masses on the periodic table for exams, you're usually seeing the average atomic mass. Why? Because many elements exist naturally as mixtures of isotopes.
Isotopes, different neutrons, same element.
Exactly. Same number of protons, different number of neutrons, so different masses. The average atomic mass is calculated considering the masses of all isotopes and their natural abundance percentage occurrence.
Like a weighted average.
Precisely. For carbon URC, you multiply each isotope's mass by its fractional abundance and sum them up. That's why carbon's atomic mass is 12.011 U, not exactly 12. Those values on the periodic table are these weighted averages.
Okay, so average atomic mass makes sense because of isotopes. Once we know atomic masses, how do we find the mass of a whole molecule?
Simple. That's molecular mass. It's just the sum of the atomic masses of all the atoms in one molecule. Multiply each element's atomic mass by how many atoms of it are in the formula, then add everything up.
Sum of the parts.
Exactly. Examples. Methane, CH, 1A atomic mass of C, plus 4A atomic mass of H, plus 4 triple beta 1 U, plus 4A 1.008 U equals 16.043 U water, HO, 2A atomic mass of H, plus 1A atomic mass of O, plus 1 pi 16.00 U at 18.02 U.
Okay, straightforward addition.
Finally, formula mass. This term is used for ionic compounds like sodium chloride, NaCl, which don't exist as discrete molecules, but as crystal lattices of ions, neuro and kala.
Right, the repeating structure.
Since there are no individual molecules, we use formula mass. The calculation is the same as molecular mass, but based on the empirical formula, sum of atomic masses in the formula unit. NaCl. Formula mass, atomic mass of NO plus atomic mass of Cl plus 23.0 U plus 35.5 U equals 58.5 UTL. Same calculation, different term to reflect the structure.
Tutors, this is where it gets truly mind-boggling. If atoms and molecules are so incredibly tiny, how do chemists actually count them? It feels impossible to handle such minute particles or such astronomical numbers directly. What's the secret?
You've just asked arguably the most fundamental question in quantitative chemistry, and it's where the mole concept truly shines. This is absolutely indispensable for every numerical problem in GE and NEET, so listen closely.
Okay, the mole.
You're right, atoms are impossibly small. A tiny pinch of salt has trillions upon trillions of ions. To handle such huge numbers, chemists needed a unit, like dozen for 12 or gross for 144.
A counting unit for atoms.
Exactly. In the SI system, the mole is the base unit for the amount of substance. It's essentially a way to count particles by weighing a sample.
Okay, how?
So what is 1 mole? Let's take this definition slowly and carefully. 1 mole contains exactly 6.0221400076 on 10 Weil elementary entities.
That huge number again, Avogadro's number.
Precisely. This number, 6.02140076 on E47, is the Avogadro constant, named after Amadeo Avogadro. To grasp its scale, imagine a mole of rupees. You could give every single person on Earth something like 90 crore rupees. It's enormous.
Wow.
So this means 1 mole of hydrogen atoms equals 6.022 times 10 molecular molecules. 1 mole of nanometer formula units equals 6.022 by 10 soaring other molecules.
So a mole is always that specific number of things.
Always the same number of entities, yes, whether atoms, molecules, ions. This fixed number connects the microscopic atoms to the macroscopic grams.
Yep.
Building directly on this is molar mass. It's simply the mass of 1 mole of a substance expressed in grams. And here's the wonderfully practical part. The molar mass in grams per mole, gmol, is numerically equal to the atomic molecular formula mass in U.
Wait, the number is the same, just different units.
Exactly. Molecular mass of H0 and 18.02 U. Molar mass of H0 equals 18.02 gmol, meaning 18.02 grams of water has no molecules. Formula mass of NaCl equals 58.5 U. Molar mass of NaCl equals 58.5 gmol, meaning 58.5 grams of salt has no formula units.
That's super useful. It becomes Zmol.
It's fundamental. It lets you convert between the mass you can weigh and the number of particles involved in reactions. Absolutely critical for all stoichiometry, #JET, percentage composition, and chemical formula determination.
Knowing which elements are in a compound is one thing, but how do we know their exact proportion? And how does that help us determine the actual chemical formula, which seems like a big deal in our syllabus?
Excellent point. That's where percentage composition comes in. It's vital. If you have an unknown compound, finding the percentage by mass of each element is the first step to figuring out its formula.
Yeah, right.
And even for known compounds, checking the percentage composition is a way to assess purity. Does your sample match the theoretical percentages?
Right, like quality control.
Exactly. The formula is straightforward. Mass percent of an element, total mass of that element in the formula molar mass of the compound at 100.
Good.
Let's do quick examples. Water, H0. Molar mass is 18.02 gmol. Water H0, H equals 2.00, H equals 2.0160 is 11.18%. Water H0, mass of O, 16.00 grams, master's OA is 16.00, 18.00, 18.0, OA 18.2. It's 88.79%. They add up to 100%.
Ethanol, CH0H or CO show. Molar mass of 46.068 gmol. Ethanol CO shores or CH shores. Mass of C equals to 2.01 G equals 24.0 J for Geme. Mass of H is 24.0 G, we're 24.02, 46.068 is 100 at 52.14%. Ethanol, CHOH or CSOs. Mass of H is 16.00 G equals 6.00 G. Mass percent H equals 6.006 per 0.68 is 100 euros, 30.73%. Again, adds up. Okay, simple calculation once you have the molar mass.
Knowing the percentage composition is the bridge to finding the formula. Which brings us to empirical formula versus molecular formula.
Right, what's the difference again?
The empirical formula is the simplest whole number ratio of atoms in a compound. For glucose, CH0, the ratio of CHO is 6.12.6, which simplifies to 1.2.1. So the empirical formula is CHO.
Simplest ratio.
The molecular formula shows the exact number of each atom type in one molecule. For glucose, it's CHO. It's either the same as the empirical formula or a whole number multiple of it.
Exact number. Got it. So if we have the percentage composition, how do we work backwards to find these formulas, especially the molecular formula? This is often a tough type of problem for GEE, and I can easily get lost in the steps.
You're absolutely right. This is a very common and important numerical problem type. It combines several concepts. Let's walk through the steps slowly. We'll use a typical exam-style example conceptually. Compound with 4.07%, H 24.27%, CS 71.65% vial, and molar mass 98.96 gmol. Detailed math and notes. Step 1. Convert mass percent to grams. Assume 100 grams of the compound. Then percentages become grams directly. H 4.07 grams, C 24.27 grams, Cl 71.65 grams.
Ready for step. Assume one or more.
Step 2. Convert grams to moles for each element. Divide the mass of each element by its atomic mass from periodic table. Moles H equals 4.007 gmol equal 0.031 mol. Mole AC equals 24.27 grams, 12.65 gmol, 2.001 gmol.
Grams divided by atomic mass gives the moles.
Okay. Step 3. Divide by the smallest mole value. Find the smallest number of moles calculated. Here it's 2.021 mol. Divide all the mole values by the smallest value. H 4.04, 2.021, and 2.021. AT from Cl 2.021, NT21, AT2, E pril ClO. This gives the simplest whole number ratio. Crucially, if you get something like 1.5, you must multiply all ratios by 2 to get whole numbers. Example free. Don't round prematurely.
Okay, divide by smallest to get the ratio. Watch out for fractions.
Step 4. Write the empirical formula. The ratio HCCl is 2.1.1, so the empirical formula is CHCl.
Empirical formula, CH2Cl.
Step 5. Determine the molecular formula. Needs empirical formula CHCl and molar mass, given as 98.96 gmol. A mass of CHCl yield 12.01 plus 2 NEU 1.08 plus 35.453 at 49.48 gmol.
Okay, mass of the empirical formula. B. Find N. Divide molar mass by empirical formula mass. N, given molar mass, empirical formula mass, 98.96 gmol, 49.48 J N, let's be a whole number, N and Euler mass, empirical mass, here N2C. Multiply empirical formula by N. Molecular formula, CHSO, CH0. So molecular formula is C2H4Cl2.
Got it. This step-by-step process is your reliable method. Practice it until it becomes second nature for those exam questions.
All right, tutor, this is where we bring everything together, isn't it?
Right.
Calculating how much of substances reacts or is produced, what exactly is stoichiometry, and why is it such a cornerstone of chemistry?
You've perfectly captured it. Stoichiometry is indeed where all these concepts converge. The word itself is Greek. stoic element plus metron measure. So basically, stoichiometry deals with calculating the amounts, masses, sometimes volumes of reactants and products in chemical reactions.
Measuring elements in reactions.
Exactly. It's about knowing how much is involved, indispensable for labs and industry. But before any calculation, the equation must be balanced.
Balance equation first, always.
Always. A balance equation follows the law of conservation of mass, same number of each atom type on both sides. It's a blueprint packed with information. Let's use methane combustion, common in exams. CH0 plus 2-CoG plus 2H0.
Okay.
Look at what this tells us. Reactants, CH0, and products, CH0, state 0, means gas, S, solid, L, liquid, aqueous. Stoichiometric coefficients. The numbers in front, 1 for CH, 2 for OO, 1 for COO, 2 for HO. These represent number of molecules. 1 molecule CH0 reacts with 2 molecules ORs, etc. Crucially, number of moles. 1 mole of CH reacts with 2 moles OR, etc. This is key for calculations. For gases, same at T, volume ratios. 1 volume CH0 reacts with 2 volumes ORs, etc. For example, 22.7 LCH0 reacts with 45.4 arrows at STP. Using molar masses, mass relationships, 16 GCH reacts with 2 plane 32 64 GROs to give 44 GCH and 2 plus 6 6. Note mass is conserved. 16 plus 64 80, 44 plus 36 beats 8.
Wow, those coefficients tell you moles, molecules, volumes, and lead to mass.
Precisely. They are the conversion factors between substances in a reaction. Now, about balancing, let's quickly balance propane combustion using trial and error.
Say J plus H is okay.
Okay, how do we do it?
Step 1, correct formulas. Done.
Balance C atoms. 3 C on left and C, so need 3 CO on right. Say shards plus O is 3 CO plus H. Okay.
3 CO2.
Balance H. 8 H on left, and HO has 2 H, so I need 4 HOs, 4 H0. CHO has 3 arrow plus 4 8O.
4 H2O. Got it.
Balance O atoms. Count O on right. 3 O2 and the say O's plus 4 H1 in HOs. 6 plus 4 is 10 O. Need 10 O on left. O has 2 O's, so we need 5 O's. 5 2 it's 10. 3 zeros plus 4 4 arrow.
5 O2.
Verify. Left 3 C 8 H 10 O. Right 3 C 4 by 2 8 H. 3 by 2 plus 4 by 1 kills 10 O. Balanced.
Perfect.
Crucial guideline. Never change subscripts, like the 8 in COs, when balancing. Only change coefficients. Changing subscripts changes the substance. Common mistake.
Don't touch the small numbers, only the big numbers in front. Right. That makes balancing much clearer. But what happens if the reactants aren't mixed in the perfect stoichiometric ratio from the balanced equation? Do reactions just stop, or do we have to account for something else?
Great practical question. That introduces the very important concept of the limiting region, crucial for real-world chemistry and exams. Often, reactants aren't mixed in the exact ideal amounts. One is usually used up first.
The one that runs out first.
Exactly. The limiting reagent, or reactant, is the one consumed completely. Once it's gone, the reaction stops, no matter how much of the other reactants are left. It limits the product yield. The leftover reactant is in excess.
Like having lots of bread but only 2 slices of cheese for sandwiches? Cheese is limiting.
Perfect analogy. Let's walk through a classic GNET problem conceptually. Detailed math and notes.
50.0 kilograms ANO plus 10.0 kilograms H and HO, Kepler process. Find NHOs formed and identify limiting reagent.
Okay.
Step 1, balanced equation. Ng plus 3Hg.
Convert masses to moles, convert kitigene to G, then divide by molar masses. N euro 28 euro, HA or Hr.
Get everything into moles.
Step 3. Identify limiting reagent. This is key. Pick one reactant, say NR. Calculate how much H is needed to react with all the N euro using 1 mol N euros, 3 mol H euro ratio from equation. Compare required Hers with available H from step 2. If available H required H, then N euro is limiting. In this problem, you find available H is less than required. So H is the limiting reagent.
Hydrogen runs out first. Okay.
Step 4. Calculate product based on limiting reagent. The amount of NH formed depends only on the HO, the limiting one. Use the H moles from step 2 and the equation ratio 3 mol Hers to find moles of NH produced.
Use limiting reagent moles to find product moles.
Step 5. Convert product moles to mass if needed. Multiply moles of NH by its molar mass, NH17 to get the mass in grams. Then maybe convert to ketergy.
Okay, calculate based on what runs out.
This step-by-step logic for limiting reagent problems is vital. Practice it.
That detailed breakdown of the limiting reagent is super helpful, tutor. It really clarifies how to approach those problems. Lastly, many reactions happen in solutions. How do we express the concentration of substances in them? This always seemed like a whole new set of terms.
You're right. It feels like new terms, but it's just quantifying how much in solution. Most lab reactions happen in solution, so understanding concentration is fundamental. We'll look at 4 common ways. Mass percent, mole fraction, molarity, molality.
Okay, 4 ways.
1, mass percent. WW%. Simple. Often on commercial products.
Mass of solute, total mass of solution, ever 100.
2G solute plus 18 dream solvent equals 20 dream solution. Mass percent 2G 20 dream at 100 equals 10%. Straightforward.
Mass of part over mass of whole times 100. Okay.
2. Mole fraction, X. Ratio of moles of one component to total moles of all components. Unitless. Useful for gas mixtures, certain physical properties.
If moles are Na and Nb, XNA. XNA plus Nb, XNB, XO Nb, no, XO plus XNB.
Moles of one over total moles.
Okay. Molarity M. Very widely used, especially in exams. Capital M.
Mole is of solute per 1 liter of solution. Units. Mol L or just M.
4 gram NaOH, 0.1 mole, 0.250 L solution. Molarity equivalent to 0.1 mole, 0.250 L equals 0.4 M.
Moles per liter of solution.
Got it. Related concept. Dilution. Making a less concentrated solution from stock. Key, celerity. Moles of solute stay the same. Only solvent volume increases.
M-euro, initial molarity of volume. Final molarity of euro. Must know this.
M1V1 equals M2V2. Crucial point. Molarity changes with temperature because solution volume changes with T.
Temperature dependent. Okay.
4. Molality M, small m, offers advantages, especially regarding temperature.
Moles of solute per 1 kilogram of solvent. Units. Mole, K-way, or just M. Note, solvent, not solution.
Moles per kilogram of solvent. Ah, that's the difference.
Exactly. Example. Calculating molality for molarity and density, like problem 1.8, is a common multi-step problem. You find mass of solution, mass of solute, subtract to get mass of solvent, then use the definition.
Okay, needs careful steps. Key advantage. Molality is temperature independent because mass doesn't change with temperature. This is a major difference from molarity and often tested conceptually.
Molality doesn't change with temperature. Okay, that's important. Hashtag outro.
All right, we've covered a tremendous amount of ground today in our deep dive into some basic concepts of chemistry. Let's quickly recap the key insights as these are the pillars for everything else in chemistry.
Yeah, it was a lot, but really helpful.
Good. So we started with the essence of chemistry, its historical roots, especially India's contributions. We defined matter, its states, solid, liquid, gas, and how it's classified mixtures versus pure substances, elements versus compounds. Then the absolute necessity of quantitative measurement, physical versus chemical properties. The SI system, those 7 base units, their modern definitions, prefixes, very important.
Yeah.
Specific properties like mass versus weight, volume, density, temperature, and those conversion formulas.
Yeah, the measurement part.
We tackled uncertainty, scientific notation for huge Redney numbers, the rules for calculations, then significant figures, how to determine them, precision versus accuracy, remember the dartboard, rules for calculations and rounding, especially that rule of 5, and dimensional analysis for unit conversions.
Sig, figs, and rounding. Need to practice those.
Definitely. We then covered the 5 fundamental laws of chemical combination conservation of mass, definite proportions, multiple proportions, Gay-Lussac's volumes, and Avogadro's law explaining molecules. These led to Dalton's atomic theory, its postulates, successes, and limitations.
The historical laws, yeah.
Then quantifying atoms, atomic, average atomic, molecular, and formula masses. The crucial mole concept, Avogadro's number linking micro and macro and molar mass, that brilliant connection between U and GROR.
The mole concept is key.
Absolutely. We use that to calculate percentage composition, and then the systematic steps to find empirical and molecular formulas from that data, a very common exam question type.
Right, the 5-step.
And finally, stoichiometry, the power of balanced equations, calculating reactant product amounts, identifying the limiting regions, super important, and expressing concentration in solutions, mass percent, mole fraction, molarity, temperature dependent, and molality, temperature independent.
Molarity versus molality difference is important.
Very. This unit, some basic concepts, truly is the backbone for your Class 11th, JE, and NEET prep. Every single concept, balancing, moles, stoichiometry, concentration will come back again and again, just in more complex situations.
So master this first.
Exactly. Revise this thoroughly. Practice past year questions, the PYQs, based specifically on these topics. Consistency is key. And never hesitate to ask if doubts remain on this chapter. Keep learning, keep growing.
Thank you, tutor. That was incredibly clear and comprehensive. The way you broke down the numerical problem-solving steps and connected everything really made a difference. I feel much more confident about these foundational concepts now, and definitely more prepared for those competitive exam questions. Looking forward to our next session.